Okay, welcome back. This week I'm going to finish the general survival analysis before I'm moving into psychophysics. So I need to do some basically clean up and a few things explain and get it done today. And that including one example, Victoria challenged me after last lecture, but I found that that question actually relate to some of the example I'm trying to explain today. So I will connect them together. And the other things I would do is probably try to come up with a couple of homework so we can use for the next Tuesday to clean up this whole things. Hey, why is this so slow? Okay, the first homework is that did you guys did the log rank test on this one, or you didn't? You haven't done this one, right? This is in the day 1-2 Kaplan-Meier exercise, and the way how we did it is we basically using the group 2. No, using group 1 as our baseline group. So let me show you what we did here. And I just want you guys play with this a little bit to kind of review some of the stuff. So here, what we did is total, okay, you combine the two groups, two cohorts together, 16, 17 becomes 23, and then you have the total deaths is the combined deaths of the two groups together. And this is how you combine the two groups. And then when you compare the group 1 and group 2, you basically said that, okay, am I, here, every time if you still have people, right, you can say that, oh, something going to happen. Is it going to be group 1 or is it going to be group 2? Technically speaking, if it's a fair coin, okay, would it be the case group 2, group 2, group 2, nothing happened to group 1? It shouldn't be, right? It should be fair example. So I did this using group 1, and then the variation is using this to calculate the variations, okay? And so the variation is kind of like the P1 square, P2 square. And I remember I show you guys the total amount is, sorry, if I'm using this one during the computation, sorry, let me see. Hold on. That's 23. Okay, this is the other one. Okay, so what we did here is, so we have a sum of square. And the sum of square is using the total differences, okay? And when I calculate the differences, stop me anytime, okay? Because sometimes I jump too quick, is here. People look at it. I have 17 people, but then I have the event is 23, so I'm negative 6.7 behind. So if I'm using 23 minus the 17. This is a negative 6.7. So the other group should be 16. If I have one group is positive or 6.7 ahead, then I will have the other group 6.7 behind. And let me show you. The sum of square, of course, is 6.7 squared divided by the variation, and then 1 degree of freedom. That's the same thing. But here I'm going to show you two slides. One is using group 1 as the frame of reference. One is using group 2 as the frame of reference. And then both will generate this 2x2 table. Okay? And both will generate this 2x2 table. So first, let me show you using group 1 as the example. Okay, if you're using group 1 as the example, okay, everybody minus, okay, the 17 out of 33, 15, or 15 out of 27, and then you said that, okay, if I have 15 out of 27, I have that many in group 1, I have that many in group 2. Now I have 4 events, 4 deaths, okay? So in other words, look at here. Let me just focus in on this picture. Totally, I have 12 in group 2, 15 in group 1. So totally I have 27. If I have one event, just one, who are more likely to have that event? You follow me? I have 15 subjects left here and 12 subjects left here. And how many? And totally I have 27. So the more people, soldier you have, just imagine that I have 2 platoon of soldier lined up. Platoon 1 and platoon 2. And then of course there is a Thompson machine gun or whatever shooting toward the troops. Which group are more likely to get killed? The more you have, the more likely, right? So here is using the ratio. I'm using group 1 as the frame of reference out of the 27. The rest of the computation is exactly the same. This is variance computation, no big deal. But look at here. If I'm using group 2 as the frame of reference, where's my 27 case here? So this time, when I do the computation, I'm using group 2 as my ratio to calculate how likely is that. So the rest of the computation exactly the same. So at the end, when you sum them up together, if you're using the old slide, I give you 23. Using the new slide, you get is 9.2. That means the total expected value. So now if you compare the 2 table, oh, you should have 23.7 to reach that ratio. So you only have 17 events to observe. You are 6.7 behind. So if one group is negative 6.7 behind the overall average, the other group should be positive 6.7 ahead of the, yeah.
Does that like relate, if you want to like picture it, is it kind of like a parabola type of bell curve thingy where it's got like equal, it's like the center mean point?
Yeah. Well, you can consider it a seesaw ball. At the end you need to balance it. So if you compare the 2 tables, I'm talking about 6.7 for the 2, no matter what. Okay? So if this is 17, okay, and here, what I'm trying to say is this. This 9.2 is how I measure it, right? Based on this table, total is 9.2. See the red? Let's sum up all the ahead, behind. I'm 9.2. But for 9.2, that's for group 2. Your measurement is 9.2. But you have 16 events, right? So 16 minus this, you are 6.7 ahead. So if you're 6.7 ahead, you know that you don't need to calculate this 23. Because the 23 should be 17 plus the 6.7 to reach this number. You follow me now? So looking at this one I did the computation using group 1, it's 23, right? Totally is 23. See the red number at the end? So if this one, 23 calculated for 17, I'm a little behind. So you know that the other groups, the number should be 9.3. So this, let me do it this way. If this one is measured, the difference is 6.7. You know that the other one is positive 6.7. In other words, this can be estimated. 9.3 can be estimated because one group is 6.7 behind or negative. The other group must be 6.7 ahead. And how did you get this 9.3? Using 33 minus this number, or you can using 16 here. Totally, I have 33 cases, right? So I can find this 9.3 using, there are totally 33 cases. You already used 3.7. I only have 9.3 left. Agree? The other way you can calculate this is that, you are 17 minus 6.7. You use this much ahead. So how much I left here? The 9.3 can be calculated as 16 minus the 1 left. So I have 9.3. So 9.3 can be estimated in two different ways. You see that?
And how did, I know you had that there, but can you just talk one more time about how you got the 23?
Okay, and let me do it one more time. But before I do it, I would like to also use a contrast way to do it. So watch here. On this one, 9.2 is calculated, using the Excel calculated. So you know that this one got to be 23.7. How to figure out that 93.7? You can say this, right? Hey, I'm 6.7 left. So this one, I'm 6.7 short. So we can say that this one must be equal to 17 plus 6.7. Or we can do it the other way around to figure out that the number is by doing this. Totally, I have 33 cases can be played. You already used up this much. I have 23.7 left to play with. So far so good. We have two tables to play with. It's all based on the seesaw board balance of the situation. The next things you ask me is that how did I get that number? So the number, I'm also using two Excel tables to get it. One Excel table is doing this. I'm using every time I'm saying that totally how many do I have? And 17 minus over 33, okay? First, just look at the ratio behind the two. It's 17 over 33, 15 over 30, 13 over 21 is at any given time, totally how many in the two groups, and then the ratio of how many in group 1 or group 2 to play the game. You follow me? And then you say, oh, you have that to play. And then the next thing you need to say is that, so what's the number in front? You basically say, oh, I have 4 deaths. I have 1 death, 2 deaths. And then I'm saying that, okay, for that 2 cases or 1 cases, based on that ratio, how many can be yours? How many can be yours? And this time, we're using group 1 as my reference. So at the end, I'm calculating based on the group 1 references. Always group 1. I add them up together is 27 cases. And now you got that 27, sum together. So the total, here, let me do it one more time. If you do a sum of all the cases you have, you got I did something wrong.
I think you just did it a lot.
Oh, okay. It's just a test. Okay, so it's 27. Okay, 23.7. But that 23.7 cases is based on 17 as my base to play, to calculate that. And then now if I don't use that, I'm using the group 2, or the first group as the one to play the game. You just basically do the same thing. Any given time, 15 out of 30, I can play the game, and 3 happen. So 3 times 15 over 30. And 9 over 22 can play the game. So at the end, when you sum them up together, you got your 9.23. And for me, all I care about actually is not that number. All I care about is that, so what is the balance? Is that 6.7, which is 16 minus 9.2. And then it's always the same things. Hey, you inch in a little bit, I inch out a little bit. You inch in a little bit, I inch out a little bit. So at the end, totally, how much you accumulate of all the best, the deaths. If you're ahead of the curve, I'll behind the curve. And that's, I get a 2 by 2, okay? And this is the kind of like the cohort, the playing compared to 2, okay? And I would like you guys to repeat this by using the same set of data. Just play with group 1 and play with group 2. Or if you don't want to, you can fake your own group 1 and group 2 number, because if you do it right, no matter using group 1 or using group 2, you should end up with the same 2 by 2 table. Agree? Yeah.
Is that last column that's on this chart, what is that one, like, what value is that?
Oh, that is when you do chi-square, here, good questions. In chi-square, at the end, okay, you need to, okay, chi-square in design by experiment, remember, is a sum of square, right? And in a sum of square, really in there is 2 things. Is a variance of the nature versus the variance of your, let me put it this way. What is f-test? F-test is chi-square over chi-square, right? And chi-square itself is basically says that, okay, what is the natural amount of variation you allow? So now, for 1 degrees of freedom, we basically said that, ahead, behind, I'm end up with the 6.7 of total accumulation of 1 group ahead, 1 group behind. So that's 6.7 squared. I don't care if it's positive or negative. You know one side is positive, the other side is negative. So that is the variation over a scale of how much variation by doing nothing, just doing the counting. So now you're saying that this over this, okay? Chi-square is a variation. Do you want to say that, is that variation reasonable variation for that many 1 degrees of freedoms of variation? And for 1 degrees of variation, I said that, hey, you can vary for 5, if my observation is 5.31, you have this ratio, okay? If this number is extremely large, okay, that means what? You spread more, far more than what is reasonable variation. And so what is reasonable variation is 5.31. So the last column represent, okay, for 1 degrees of freedom, for this kind of data set, look at here, is sometimes you're ahead, sometimes I'm ahead, sometimes you're ahead, sometimes I'm ahead. Kind of, if you compare this 2 tables, can you see that the front is this part. The back is how many left we can play with. So it's just a bunch of ratio of square, square, square accumulated. So lump them together. That is, I'm saying, this kind of data, I can allow 5.31 of variation. And you have what, 6.7 square? Is that far more than I can tolerate, or that's okay for me to tolerate? Yeah, so if it's more, that means my two groups are different, okay? Now, actually, you're ahead of me again. So now what I'm saying is that you can play a game like this. You can build two survival function curve. Can you do that? One is based on group 1. No, the QP survival. H is the probability over. Okay? And what I did here is ignore the if I consider this is my survival, okay? I've tried to approximate the hazard function. How did I do that? Here, what is hazard function let me do it step by step. The survival function is easy, right? It's upstairs times what's the increment. Agree? You guys already done it before, right? Upstairs times this, you get your survival function. So you can survival for group 1 approximated, survival for group 2 approximated, a survival for both approximated. So now you can have 3 curves. One is the red curve, one is the blue curve, one is the green curve, which is the summation. Usually, okay, when you play, this is not a real thing. This is kind of approximation, but this approximation, why you guys think that the green curve, the sum of the two, is always between the red and the blue? Yeah, because it's kind of like the lump of the two groups. So here, if I'm holding my two sons, one in my left hand, one in my right hand, and sometimes one guy's run a little faster, the other guys will be a little slower. Sometimes my left side is a little faster, right side will be a little slower. But no matter which one's ahead, which one's behind, I should be always what? In the middle. So my green survival should be somewhere in the middle, okay? And next is how I come up with this hazard function approximation. My hazard function approximation is always using the, here, if you're using the drop, and since the dropped, I ignore the time, okay? I'm just saying that there's a drop, drop, drop at any given time. So I have this combinations of drop, drop, drop at any given time. And can you guys think about it? If the dropped, okay, is at a different rate, so that's the differences between the two drops, okay, and divided by my current rate, that basically tell me kind of like, oh, how hazard at the current survival and what is my slope. So I'm using this value divided by the differences. That will give me this curve. And this curve I'm really trying to see is what? Sometimes event 1 happens, sometimes event 2 happens. When did one event happen? And for this, I actually see what? Very quickly, I can see the blue oscillate at the beginning more. And the red kind of like oscillate at the end more. And then the green is somewhere in between. that kind of give me some anecdote about why these two groups are different. Statistics say that they're significantly different, right? And I'm trying to figure out, why is that? Is it, more event happen at the beginning, less event happen at the end? So this is kind of like just have a graphical visualization. Where is that statistics coming from? And so I would like you guys, if you want to use my data, that's fine. You don't want to use my data, you can fake a set of data because you can cross-check. No matter you're using group 1 or group 2 for chi-square 1 comparison, you should have the first double check is if one group got a high 6.7, the other group should have a low 6.7 or 6. The differences should be the same. If you got different differences, you know you did something wrong. Okay? And the second thing is that if you see the significance or you don't see the significance, have some explanations where the difference is coming from. Is it at the beginning, at the end, and so on. Okay? So that's the first things I would like to explain is that this is just kind of like using the graph to explain where the survival or where the hazard coming from. Okay? That's first exercise. And basically repeat, is your guys' slide number slide 15? Or this table is slide, what's the number of your slide? Huh? 16? Yeah. Is on your lecture note is slide 16? Okay, so using my data or create a set of data to create, okay, the log rank test, but do the log rank test, whatever the data is on slide 15. Yeah? Okay. Yeah. Okay. That's 13? Okay. You can use the data in the slide 13 or create a new data set. But when you do that, when you do the log rank table, try to do it using group 1 as the frame of reference or group 2 as a frame of reference. But no matter using group 1 or group 2, at the end, you should have the balance. Okay? So no matter using group 1 or group 2, if you don't get the same number of the differences, something wrong with your computation. Okay? And the second thing is that once you do that, statistically, you accumulate all the differences together. You want to say that, hey, is my treatment 1 and treatment 2 different or the same? Statistically, you log rank test will say significant or not significant. You're done. But after you're done, I would like you to fake a survival function and a hazard function to explain where that difference is coming from. This is not a legal approach, but a lot of time it gives you some insight by graphically representing that. That's homework due Tuesday, first thing. The second thing is this, okay?
Wait, can you slow down? So you want us to do the first chart?
I want to do this chart.
Using the data, and then you want us to do those, the hazard?
No, time out for a second. I want you to create this table twice.
Right.
First time using group 1 as references, second time using group 2 as references. No matter which group you use, you should end up with the same number. And so that is your double check. No matter you're using my data or you're using your own data, that is the holy grail. If you don't get that, you're in trouble. Agree? Okay. Second one is that I would like you to fake 3 survival functions using group 1, using group 2, using the total. And show me that the survival approximation of the total should be always kind of like somewhere in between the group 1 and group 2. Okay? Then that can help you visualize what's the comparison, log rank test comparison are doing. The second thing is that using the differences of your survival divided by your hazard function, you can approximate the hazard function. Then I would like you to visualize it and say that if our statistics, chi-square test, log rank test, show significance, means that the two groups have different hazard. Why? Can you look at the graph and see, oh, one group got more hazard at the beginning or at the end, and so on? Make sense? Okay. Can I go to the next things? Okay. The next things is Victoria asked me a questions on the. Oh, it's not here. Oh, this is the same slide set. When you plot. That's in the distribution, right? No. Should be in this one. Okay. Where is it? Ah, yes. Victoria asked me a questions about plotting the Weibull, and I'm trying to explain and saying that Weibull, when the shape parameter equal to 1, when the shape parameter equal to 1, okay, and they should be, the hazard function should be flat. So exponential distribution is a special case of the Weibull distribution. And then she just said that, but how come when I change the shape parameter or the scale parameter, everything looks so ugly? It doesn't look right. And what I'm trying to do this, actually, I think the question itself can be explained more than one value there. First, everybody agree, look at the equation ft here, the CDF here. If the shape parameter k, okay, if the shape parameter k is equal to 0, then, I'm sorry, equal to 1, then this looks like an exponential distribution, right? Agree? But in order to make this look like exponential distribution, how are you going to deal with alpha and here? How can I deal with alpha and lambda here? Look here, k equal to 1, technically speaking, to make this look like this, alpha need to be equal to 0, lambda need to equal to be 1 in order to make this guy look like this guy. Agree? In other words, is that if that's the case, where is my center? My center need to be nada. And what is my scale? Lambda need to be 1 in order to make this happen. But that's not the case, right? So what I'm trying to say here is one thing we can do is consider this as almost like a regression or transformation. And some of the stuff, actually, we have that kind of logics at the end of the at the end of our after we talk about psychophysics. So what I'm trying to do here is this, okay? Pretend here I have a z, okay? I have something I call z-score, okay? And the z-score, suppose, okay, let me do it here. Can I open that? Okay, so let me do it here. What if, okay, my t-score is equal to, okay, my t-score is equal to a value, I call it t prime, or t prime minus, give me a value, z-score value, center mean at, say, 3 or 4. So this should equal to t prime. My t should equal, okay, let me do it here. Oh, I did not define that yet. So let me, okay. Let me do it this way. T equal to t prime minus 3. So t and t prime, the difference is 3. So t prime should equal to t plus 3. Agree? And then I can make this even uglier. T equal to t prime minus 3 divided by 2. So t equal to t prime minus 3 divided by 2. So if t is perfectly exponential distribution, I know t is not the original t. T is from something else. But after I clean up, it will look like that. Look like t is exponential distribution. So if looking at this, that means t prime is a regression. And this regression should equal to what? 2t plus 3. Agree? So if I have a 2t plus, my t prime is 2t plus 3, that means my t should look like this. So I can have some observation and say, hey, I have something called t prime. And this t prime is equal to 2 times t plus 3. So if I have this, okay, and if you try to plot, okay, and you try to plot this guy, it said, hey, I don't want you to plot I don't want you to plot this one. I want you to plot t against this, ht. I want you to plot t prime against ht. How come I don't have it? Oh, I know.
It was on the original T.
Yeah, I didn't shift it, right? Yeah, so if I just shift it here, okay, I will still have the same thing, right? But if I played the tricks and said, don't plot this guy, I want you to plot this guy. Guess what you're gonna, you have to get rid of the other stuff. But no, let me do it this way. Create a new one. Okay, so if, say I want to plot this against this, okay, and I'm just saying, okay, move over here. That's your flat HT, right? But then I'm just saying that, no, I don't want you to have that flat one. I want you to plot against the original one. You're going to see some change, okay? Next, that's not what I'm trying to show you here. What I'm trying to show you here is in real world, what we usually what we'll do is we have the t problem first, and then I've tried to generate my t. And what will be my t? My t will be equal to whatever my observation minus 3 divided by the scale parameter 2. Okay, and then you should gradually see this and this exactly the same. So now I think I explained why you didn't have the flat line, but what I'm saying is that there are deeper meaning in the question you asked me. What is that deeper meaning? The deeper meaning is this. A lot of time, we're going to end up saying that, oh, I would like you to generate a hazard function. And the hazard function, remember, we said is a regression. And when we try to do the regressions, the time itself actually already have the, I'll call it, oh, I already have a scale parameter. I already have a shape parameter. And whenever you need to model and say that, oh, what is this distribution going to look like? You really is not just trying to find the beta 0, beta 1, beta 2, beta 3. You also need to find the shape parameter, the scale parameter, the shape scale, and the center parameter. Okay? And I'll have another exercise coming in for you to play with. But before you do that, I would like you to look at this, okay? SAS is the things that we probably in 2 weeks or 3 will getting into. So I'm just asking the school install SAS on this computer, but 213 got SAS, okay? And if you cannot use the school's computer, you can download SAS directly to your computer. But you make sure your computer is big enough. Otherwise, it's not going to be easy to download. Okay? So to download SAS, okay, I would like you to download the following 3 procedures. One is called life regression. Okay? So not the procedure, the support. So when you have this, you will see their manual. Usually each one of them is about 100-some pages. Okay? And for this one, I'm going to go to shape. Okay? See here? There will be a Weibull shape parameter. Later, SAS will help you estimate. And look at what's the besides shape parameter. You have a scale parameter. And what is that scale parameter? Your lambda divided by 2 divided by 3. So right now, we're just saying, hey, give me a set of data. And then I use that step function to figure out the hazard function graphically, how it looks like, right? And later, what we really want SAS to do for us is not only doing that, help me find the scale parameter, the shape parameter. I give you a set of data. You can use few parameters to describe the data. And that's the goal here. See here? There's gamma distribution. And look at gamma's distribution. They will have shape parameter, scale parameter, and then I think they have another parameter you need to estimate. There are Weibull shape, Weibull scale. There are natural shape, natural scale. So please download live regression manual. The next manual I would like you to do is download live test manual. And when you download a live test manual, okay, same thing. Let me help you look at it, and you will see something familiar. Have you ever seen this kind of curve before on the screen? Survival function, drop, drop, drop. So, like I said, when things getting busy. We're not going to do a lot of Excel. That's too labor intensive. We'll let SAS do it. But at least if someone challenge you, hey, how this thing is done, you can do it by yourself. Just do the demonstration. And what will be the comparison here? Product limit. Are those two curves the same or different? Follow me? Okay, so you need to download SAS procedure. You need to download live regression and live tests. And look at this. You will basically try to say that, okay, is the hazard function monotonically increasing, decreasing, or constant? Okay? Okay, the third procedure you need to download from SAS is called PHREG, proportional hazard function. Okay, and proportional hazard function look a lot fancier because there are tons of stuff. This is the one that we're going to spend a lot of time to explain. Okay, and this three procedure, please put that down. Okay, usually we call live test, we call it non-parametrics technique. Because why is non-parametrics? I don't care what's your shape parameter. I don't care what is your scale parameter. All I care about is what? Hey, is this thing's monotonics? Going up, going down? Just looking at the graph. That's called non-parametrics. So live test is just looking at the picture and figure out the story. We call live test. The other one is called live regression. Live regression is a parametric technique. We're going to use regression to figure out all the parameters. So everything's, you can just consider, when you look at regression, you feel like is, oh, increase X by this much, my beta will increase, say is 2 times X1. So every time X increased by 1, the total contribution will be 2 times 2 times 3 times 4, increase with the X. And then so everything will contribute to your hazard function or your life according to those parameters. And how to find those parameters, SAS will do a lot of job for you. And right now I'm still trying to warm you up with the SAS, the Excel way to look at things. Because sometimes SAS doesn't, SAS is very powerful, so SAS sometimes give you an illusion, false sense of security. You always get a number, and you think that, oh, I get a number, especially p-value less than 0.05. I must have done something right. But it could be, garbage in, garbage out. So I need you to download PHREG, because PHREG is called semi-parametric techniques. So semi means it's not purely parametrics, it's not purely non-parametrics, it's somewhere in between. Okay, download those three procedures, and if you don't do that within 2 weeks, you're going to pay the price because we're going to use a lot of SAS. Okay, next, I would like to, so far so good? So next things I would like to do is finish the things that I wasn't doing too well last week, Tuesday. Okay, on Tuesday, do I still have that Excel file from last time? Where is it?
Is that all for the homework?
Huh?
Is that all for the homework?
Yeah. Uh-huh. Okay. Yeah. Okay. So for the homework this week, one more is that, what?
I already sent it. No.
For next Tuesday?
Yeah.
Oh,
Is this for Thursday?
okay. Okay. No, we need to, oh, Tuesday homework you already announced?
I just sent it to you.
Oh, the part,
Yeah.
let me see how much, if there's enough material. Hey, you know, hurricane is coming. You cannot do anything. Huh? Well, okay. The things I would like you to play with is some things. First, play with the log-odds ratio and show that when you change the number, okay, the shape will change, and then the p, the odds. Okay, let me plot it. From first one of the day 1-3, okay, and day 1-3, you all I want you to do is to see this, okay. If you consider this capital B, EB is the B is a intercept plus a slope, so. Think about it. Does this look like what she just asked me for her last homework? Why? Because I have a term. In that term, I have a something something. But when I lump them together, I'm just calling it, oh, that's my B, right? And sometimes we just lump them together. That's my scale. That's my shape. But I know that when those parameters changed, my whole my whole things will change accordingly. Okay, and here I do want to ask you why a lot of time we like log so much, because see here, look at this curve. Transfer function 0 to 1 ugly. 1 to 0, ugly. Odds as an elbow function, still ugly. When the things looks really nice. When you put a log on something, it becomes a straight line. So once it becomes a straight line, what can you do? You basically said that, oh, I don't care whatever you're talking about. Could be y can be expressed like a straight line. Could be log of and odds can be expressed like a straight line. Could be your hazard function can be expressed like a straight line, or you know, in queuing theory or your arena, you could have your customer arrival rate. Depends on, oh, is a festival today? Is or something special today? Remember I told you guys how I used to work for an insurance company? And what will be something would like to ask the doctor in the emergency room? When you expect a lot of accident? Sunday night, Monday morning? Are they the same reason or different reason? Sunday night rush to get home. Monday night after 2 weeks hangover, 2 days hangover, you just don't drive well on Monday morning in a rush hour. So things could happen. And the other thing is that when you think day by day, the circadian rhythm gonna ruin people, and people tend to have accidents. If I tell you 2 p.m., 3 p.m. in the afternoon, do you believe me? Why 2 p.m. in the afternoon? People, no, drowsy, they want to take a nap, getting tired, okay? And so traffic hours or certain things tend to happen. So we're basically trying to say that now, hey, the hazard over time could be a function, and we'd like to find that function, okay? And the things I would like to tell you is that no matter HT or survival function, if the function, they all look like PDF, CDF, they all look like a bunch of exponential. What's the beauty of exponential? exponential over exponential, they can cancel each other out. So I did this last time. I said that, oh, here is the hazard for the Cox regressions combined over time. And the one I would like to show you is where's that example? Okay, this example is about fracture with female taking OC. And so here are a bunch of OC example. And then see here, you basically have fracture event 1, fracture is an event, fracture is an event, fracture is an event. At time 6, okay, there's one fracture, but this fracture is the patients or the female did not take OC, so did not stop taking OC. So at time 6, I'm really trying to say is that, no, I don't have a time 6 case here. Time 6 here is at the very beginning. I'm only at the very, very beginning. I don't know what will happen afterward, okay? So at the beginning, my partial, LP means partial likelihood. You don't need to look at anything behind. The second multipliers, third, and fourth, you don't need to look at them. You only look at the first one. First one, when I have the fracture, totally, all I know is that how many people are taking OC, how many people are not taking OC. I have 4 people not taking OC, 3 people taking OC. So all I can say is that I assume taking OC and not taking OC will change their beta. So they will have a beta based on OC or not OC. But then I say that, oh, I have my first case. The first case is what? It's from the 3 or from the 4. It's from the 4. You follow me? There are you can have boys, girls, and then, oh, this accident from boy, from girls. But this one is from this group. And then after that, first one out, so we know that, and after that there's a sensor. There's no OC just left. So I don't have that case. But I can have a second one is here. So now my multiplier at time 12, I got 2 terms. First event times the second event. And this time I'll have totally 5 cases left, right? 1, 2, 3, 4, 5. I have 5 left. And among the 5, I have 2 taking OC. I have 2 taking OC and 3 not taking OC. But this case, C is upstairs, is taking OC or not taking OC. Is 1 was taking OC. So it's from these 2 groups. So this is my partial likelihood for time 12. And then on time 17, time 17 is already here. 17 is what? How many left? 4 subjects. 2 taking OC, 2 not taking OC. But this time, this case is from the female taking OC. So 17, history, new one, and taking OC or not taking OC. So it's kind of like every time partially using whatever available, accumulate. And then finally, when you combine all the partial likelihood together, you're still doing the same things. You're trying to figure out that, let me find a set of parameter. Make every estimation as big as possible. That means you fully utilize the number. Okay? I'm going to have some psychophysical exercise later to show you Excel example as change the number, make it big, make it small. So for some people, okay, doing fuzzy logics, they are using language to do the same things I'm doing here. But in psychophysics, we're still using probability to approximate feeling. Which one is more likely, which one is less likely, and then at the end, You just try to say that here are a bunch of numbers, and I would like to fully utilize all the numbers. So you say that, oh, if I play with this number from 1.1 to 1.2, every estimation, partial likelihood, getting bigger and bigger. That is a good number to use. So it becomes an optimization problem. Find a parameter to make every partial likelihood as big as possible. One more thing that I did not explain, which is very important here, is that sometimes in statistics, let me see if I have it. Okay, no, I don't have it here. Let me see. Okay. Here. If I'm trying to say that I have a proportional hazard for every event to estimate the ratio, right? Do you think that I can also do the same things for sensor data? I can do it for sensor data because I can say is that, hey, at certain time 12 or time 17, I open up, check on him, and he left or she left. That's fine. But at least I know that when I check at that time, his survival function at that particular moment is also, one of our potential expressions, something exponential exponent of x minus some alpha value divided by lambda. Whatever those parameters I need to estimate, I don't know, but I know that that observation at time 12 or at time 17 is a sensor data, but the survival function is valid. So now you become a technical example. Let me see if I can find it. Way up here a little bit. Give me a sec. Here we go. If I have a bunch of partial likelihood, and they're all about something over a bunch of, taking the drugs, not taking the drugs, smoking, non-smoking, whatever you're doing. When you multiply these whole things together, there are two different ways to express this. One is hazard over hazard. One is survival over survival. And then you just write the whole things almost like this. Let me see if I can do it in a new slide. Okay? You basically said that my LP function, partial likelihood function, will be written like this. Okay? A bunch of, I would say, yada, yada, yada. Okay? Over summation of a bunch of this. And this is, you guys see that, right? We have our hazard function previously, remember? At any given time, proportion of a bunch of smoking, non-smoking, taking OC, not taking OC. But then we will always have this multiplied by another function. It also look like this. Okay? And this time, let's just don't call it dot, dot, dot. We just call it column, column, over column, column. And if it's about hazard, we'll use this ratio. If it's about censorship, we'll use this ratio. But the problem is that, hey, you investigate this person only once. Either she got censored out, or he got censored out, or he is an event. So at the end, we'll create a delta function. Okay, I'll just create a delta. And this delta function, where is my symbol? Okay, this delta function need to be up here. What do I mean by that? The delta function will be 1 or 0. Because if, here, and over here, I'll write it one more time. A little bigger. Okay. So every time the partial likelihood is a multiplication of the two kind of cases, either the front, a bunch of hazard over hazard, or a bunch of censor function, survival over survival. So the delta is a number either 0 or 1. Because if this delta is equal to 1, okay, these things exist. 1 minus 1, these things become 0, become 1. Because 1 minus delta is equal to 0, so the power of this side equal to nothing. So it means this is a hazard case. And if delta equal to 0, means what? Is a survival case. So we can use this to say that, oh, let me use this data point. Oh, this is a sensor data case, or this is a survival data case. And that way we can fully utilize the data to calculate the partial likelihood. Okay? And that's what we're trying to do here. And since you're the only one left here, we're going to continue this lecture for another 3 hours. Okay? See you next time.